So now let's look at some applications of using this concept of the mole for counting things in chemistry. We'll look at this through several problems. The first one asks how many hydrogen atoms are present if you have 3 moles of NH3 or ammonia. We're going to solve this two different ways. One, I'm going to show you a step-by-step way of thinking about how to address this question, and then we're going to show you the quick way of doing it using the dimensional analysis technique. So first of all, what does this formula tell us? Well, it tells us that for every molecule of ammonia, it consists of 1 nitrogen atom and 3 hydrogen atoms, right? So we can use this as a conversion factor, 3 hydrogen atoms per molecule. If we now ask the question, if we have a mole of ammonia molecules, how many actual numbers would we have? Well, I hope you would answer with 6.022 times 10 to the 23rd. It's just a definition of a mole, right? We're just counting things. Here the mole is a set, here's the actual number. Now, if we ask the question, how many molecules do we have in 3 moles of molecules? Well, I hope you would see that all you need to do is take the number of molecules here and multiply it by 3, right? Which would give us roughly 18 times 10 to the 23rd, and convert that to standard scientific notation would be 1.8 times 10 to the 24th ammonia molecules, right? Now, what the question's asking here is how many hydrogen atoms are present? Well, if we now know the number of molecules we have, and we know that there are 3 hydrogen atoms per molecule, you just take this number and multiply by 3, and we should roughly get 5.4 times 10 to the 24th hydrogen atoms. So that addresses the question. Now, let's take a look at solving this using the dimensional analysis technique. Looking at our problem, this is what we're given, 3 moles of ammonia, so we start there. We're going to multiply this by some conversion factors, which ultimately is going to give us the number of hydrogen atoms. So the first thing we need to do is convert from moles of ammonia to molecules of ammonia. That's essentially what we did right here in this step, right? So we use this conversion factor for the definition of a mole. That allows our moles of ammonia to cancel, and if we stop the problem right now, we would have calculated the number of molecules of ammonia, which we established earlier is just 3 times 6, right? Times 10 to the 23rd. To count out the number of hydrogen atoms, we need to use a second conversion factor, which is 3 hydrogen atoms per molecule. So we do that, and again, just like we showed you initially, we just take 3 times this number times 3 again, and we will get out 5.42 times 10 to the 24th hydrogen atoms. Now, in the previous problem, we showed you that if you know the number of moles of something in chemistry, you can count out the actual number of various components in it by using the definition of a mole, which is Avogadro's number. You can count not only formula units and molecules, but atoms, ions, a variety of things. So we're going to look at this again in a different problem, as well as another important conversion factor, which is the molar mass, right? Which is just the mass associated with 1 mole of something. That allows you to go back and forth between the mass of a substance and the actual numbers of things in these sets called the mole. So let's look at this first question. What is the mass of 3 moles of copper? So you're starting here in the problem, and you're going to use the molar mass as a conversion factor to go from moles to grams. So using the dimensional analysis technique, we start off with what we're given, 3.0 moles of copper, and we need to figure out the mass in grams. So we need to use the molar mass, right? So if we take this, we look up the mass in 1 mole of copper, we'd see in the periodic table it's 63.546 grams, and we use our conversion factor in this way so that our units cancels for moles of copper. So we essentially multiply 3 times this number, and we end up with this value. Keeping track of the number of significant figures is 2. That's where we've underlined it. So if you wanted to report this number, you would round it off to 190 grams of copper. Now, if you recall back in Chapter 1, we showed you that this dimensional analysis technique is basically just doing algebra. So for example, you could solve this using the ratio method. 63.546 grams of copper is to 1 mole of copper as x grams of copper is to 3 moles of copper. Solve for x. This is exactly the same type of problem. All right, let's look at the opposite problem. Say we know, say we've gone in the laboratory and we've weighed out 190 grams of copper. How many moles of copper would we have? Well, we would start here, use our molar mass to calculate the number of moles. So we start with 190 grams, but instead of multiplying by our conversion factor or molar mass, we divide by it. Okay, so we simply take our ratio and take the reciprocal, and now grams of copper cancels, and we've got moles of copper, right? Which we now round to 2 significant figures, be 3.0 moles of copper. All right, so let's put this all together. Let's say you're given 190 grams of copper and you want to figure out how many atoms of copper are present. What you're going to need to do is take your mass information and convert to sets of copper atoms in terms of moles. And once you've calculated the number of moles of copper atoms, you can use Avogadro's number to count out the actual number. So it's a string of 2 conversion factors. Let's start off with what we're given, 190 grams of copper. Right, just as in the previous exercise, we're going to want to divide by the molar mass and then multiply by Avogadro's number. Right, so in this case, our units cancels here, grams of copper, moles of copper cancels, and we have our answer. Rounded to 2 significant figures. 1.8 times 10 to the 24 copper atoms are present in 190 grams of copper. On Monday, in our class period, we're going to look at these 4 problems. You should try to work these on your own before class, and we're going to show you don't need a calculator at all to do them. So to close out this lesson on using the mole for doing calculations in chemistry, we're given the problem that's typical of an exam problem, is to figure out how many oxygen atoms are present if you know the mass, 12.3 grams. So the first thing that you need to do here is to collect your conversion factors that you're going to need to solve the problem. So we need to know the molar mass, and we need to Avogadro's number. So the mass in 1 mole of oxygen, if we count it out, 1 mole of oxygen molecules, it's going to weigh 32 grams, right? Because we have 2 moles of oxygen atoms total. Each one is 16 grams. In addition, we have the definition of a mole, which is 6.022 times 10 to the 23rd oxygen molecules in 1 mole. So we begin our problem then by writing out what we know, 12.3 grams, and where we're trying to get to, which is the number of oxygen atoms. So the first thing we need to do is use our molar mass to convert from mass to moles of oxygen molecules. So that's shown here, right? So we put the mass of oxygen on the bottom to allow our units to cancel, and at this point we would have determined the number of moles of oxygen molecules that are present, 12.3 grams. But the question wants us to address how many oxygen atoms, so we need to convert this to the actual number of molecules, right, using our second conversion factor, which is just Avogadro's number. Again, moles of oxygen cancels, and at this point we will have calculated out the number of oxygen molecules present, 12.3 grams of O2, which will be, when we round off to 3 significant figures, 2.31 times 10 to the 23rd molecules of oxygen. Now, if you answer this on your test, it would be wrong. Why? because you didn't read the question carefully. The question is not asking you how many molecules of O2 you have present. It's how many oxygen atoms total do you have. Now, if we look at this, we know we've counted out the number of molecules of oxygen. There's 2 oxygen atoms per molecule. So if we just take this value here and multiply by 2, all right, 2 oxygen atoms per molecule, we will get the right answer, which is 4.63 times 10 to the 23rd atoms of oxygen. So folks, pay careful attention to what the question is asking when you read your exam problems. And so the last thing I want to address here before we finish this lesson is that if you pay close attention to the dimensional analysis and you write out not just these numbers, but the units and exactly what things you're representing, right? So in this case we had molecules of oxygen here. Here we have atoms of oxygen. You can always go back and look to make sure that you've addressed what the question's asking. You can't do this if you just pick up your calculator and start banging away. You're better off using the discipline of writing everything out just as shown.